The title of my article is A Channel Estimation Scheme of Short Packets in Frequency Selective Channels. It is mainly divided into the following parts. The first part is the introduction. A growing number of devices connections promotes the development of IoT technology. In the field of IoT, MTC is a hot research topic recently. The length of data sent by MTC is short and not fixed. The key requirement of MTC is to achieve low delay and high reliability. In this article, we focus on two things. The access of a large number of devices will cause interference to the reception of target devices. One solution is to introduce interference training circles. When the packets are short, the training circle must be kept small, which will cause a serious decline in the quality of channel estimation. Moreover, fewer polys will reduce the quality of channel estimation. The second is the design of recovery receiver for transmitting short packets and a high-speed background. In this situation, the stability of vehicle transmission link and the quality of transmission data are greatly reduced. The second part is system model. We consider the uplink communication of high-speed moving vehicles in the urban background, such as the collection of vehicle information via wireless sensor network, the reporting of vehicle quality, and whether the driver's driving state conforms to traffic rules. Assuming that the sensor of the target vehicle has an antenna, the received signal contains not only the required information but also the interference from the sensor of the adjacent vehicles. There are interference sources in the communication process. Assume that the total number of data transmission is n. ND is the number of data transmission, NP is the number of traditional plate, and NF is the FFT points for OFDM transformation. The received data can be expressed as YR, where YR is unobserved values received. XT is the signal emitted by the target vehicle. TRT is the data transmission matrix of the target vehicle. The third part is joint channel estimation. We use traditional polit and virtual polit to conduct channel estimation to improve the quality of estimation. The workflow of the whole system is shown in this figure. Firstly, channel estimation is performed using traditional polit for the obtained signal. Secondly, the decoded data is used for interference reduction operation, and then the virtual polit and the traditional polit are selected for channel estimation. Thirdly, the data is decoded by the re-estimated channel, and the above process is repeated until the conditions are met for output. The selection of virtual polit is to select a small number of reliable data symbols from all available data symbols for channel estimation. The traditional polit observation value of the target vehicle is YP, where PT is the polit sent by the target vehicle. YP is the polit receiving value. With the increase of NP, the quality of channel estimation increases gradually, and the estimated channel vector converges to perfect channel knowledge. But the short packets contain fewer polys. The channel estimation quality will degrade. In order to improve the quality of channel estimation without increasing polyt overhead, we use virtual polyt to re-estimate the channel. When the number of virtual polys selected is ns, the received value can be expressed as ys, whereas t is ns virtual polys selected from the data samples sent by the target value. ys is the observed value of the received data. The traditional polyt observation vector yp is combined with virtual polyt vector ys to obtain the observation vector yc. Note that the second item in this equation is not the signal from the transmitting antenna, but the interference. We can conceal the interferences by this equation, where the estimated of interstream interference is constructed from the soft intermediate of the data samples Si, and the channel estimate DRI obtained from the previous iteration. We use YC, PT, and SI for RS channel estimation, where each RS is the estimated value of the RS channel parameters. Hence, the MMSE channel estimation matrix is DRT, where the white vector can be expressed as W. The quality and quantity of virtual polyt will directly affect the quality of channel estimation. The best way to select virtual polyt is to compare the performance of all virtual polyt signals and traditional polyt signal combination, and then compare the smallest MSE. We adopt a simple method. We only use a signal sample to analyze the MSE and then choose a virtual polyt symbol. The nth data sample is used as a virtual polyt and its MSE metric is expressed at epsilon. We consider the case that the traditional polyt interval is very large, so the correlation between polys is very weak. In the case of high SNR, we can prove epsilon. And the first part is simulations. We consider the case that our polyt distribution mode adopts the diamond-shaped polyt pattern, and each resource block has 12 subqueries with a subquery interval of 15 kHz. There are 14 data symbols in the time slot, and various modulation methods are used. The channel is modeled as an extended vehicular A-channel model, with the vehicle speed set at 100 to 200 km per hour, and the Doppler mode introduced as the Jackie's model. These two fingers shows the distribution of traditional polite data and virtual polite frequency. The finger on the left shows the distribution of small interference from adjacent vehicles. The quality of soft decision has a great influence on the selection of virtual polite. Meanwhile, the correlation between the virtual and traditional polite also affects the choice of virtual polite, most of which are located around the traditional polite. When the interference is large, the virtual polite frequency distribution is shown in finger on the right. The correlation between virtual polite and the traditional polite have a significant effect on the choice of the polite, and virtual polites are distributed around the traditional polite. It is well known that the signal distributed around the traditional polite is of better quality at recovery. The finger shows the performance of different channel estimation algorithms at high SNR. The LS method is worst for channel estimation compared with flat slow fading channel. LS estimation has worse performance than MMSE in selective fading channel. It can be seen from this finger that under the condition of high SNR, the proposed method can obtain a gain of about 2 dB, and the channel estimation performance is gradually approaching the perfect channel knowledge. In the case of low SNR, the simulation results are shown in this finger. As can be seen from this finger, our proposed method only has more gain. This paper adopts a cyclic iteration method to eliminate multipass interference to improve the detection performance and the low SNR. The result is shown on the right finger. This is interference elimination algorithm. We can improve detection performance by this equation, where I is in integration step. Firstly, using MMSE algorithm to obtain the estimated channel transmission matrix DRT. Secondly, recover the signal according to the channel transmission matrix by YRT divided by HRT. Thirdly, initialize with I equals 0. Fourthly, interference cancellation by subtracting diagonal elements of matrix. Fifthly, improved estimation of transmission matrix DRT enabled by a reduced interference at the polite positions. Sixthly, update the recovery signal. Seventhly, repeat step 4 to step 6. We consider I equals 8. This finger shows the comparison between the method of randomly selecting the virtual polites and the method of selecting the virtual polites using our equation. The simulation results show that the random selection method can achieve better results in channel re-estimation because of the low quality of soft decision. The fifth part is conclusion. In this paper, we analyzed the receiving mechanism of short packet transmission under high speed and frequency selective fading channel. We effectively saw the decline of channel estimation quality caused by interference training period and less polite number of short packets. And because the transmission performance of the proposed method is not improved significantly at low SNR, our algorithm to eliminate the influence of multipass can improve the bit error rate performance. Thank you all.